researchers who are attending this session from India, Southeast Asia, and Middle East Asia. Thank you all for finding the time and visiting our today's webinar. This webinar is organized in association with Brettel Manufacturing Incorporated, USA. My name is Sachin and I am a Sales and Application Engineer at TESCON. About our company, TESCON is a leading distributor of research instrumentation for study of various aerosol properties like size distribution, chemical composition, etc. Also, we have a cutting-edge instrumentation for study of cloud aerosol interaction. TESCON provides aerosol measurement products manufactured by Brettel Incorporated for India and some part of Southeast Asia. Today we are presenting hygroscopic growth and its effect on physical and chemical properties of aerosol, which will be presented by Dr. Fred Brettel. So Fred is a CEO of Brettel Manufacturing. His R&D focus mainly developing small-sized and cost-effective instruments to measure aerosol physical, chemical, and cloud nucleating properties. Just a little housekeeping before we get started. If you have any questions during the presentation, please type it into the chat box. I will bring them up after the presentation. Also, we will have a 10-minute question and answer session at the end of this presentation. If you are facing a poor video or audio quality, please click on the Reconnect tab, which is at the top of your window. You can watch our previously conducted webinar and download the presentation file in the blog section of our official website. Thank you again for joining us. I request Fred to start this session. Fred, over to you.
Thank you, Sachin, and I appreciate the introduction. Good afternoon to everybody in India. As Sachin mentioned, my name is Fred Brettel. I'm the CEO and owner of Brettel Manufacturing here in the Silicon Valley in California. Today, I'm going to talk about aerosols and water, specifically focusing on science applications in climate, but just discussing generally the role of water in determining aerosol physical and chemical properties and how we measure that. I'm going to start by giving just a few real-world examples of the interaction between ambient aerosols and water. So just to bring everybody up to the same point, we're surrounded by aerosols, as many of you realize. They're everywhere we go. And aerosols interact with water vapor continuously. As the relative humidity in the ambient goes up and down, usually on a diurnal cycle, aerosols are accumulating water through condensation, and water is evaporating from those aerosols. So water actually is the most common chemical constituent of the ambient aerosol. And even though that's true, we still do not have simple measurement techniques that allow us to measure directly the content of water as a function of relative humidity on the ambient particles. This picture shows Mexico City back in 2006, a photo taken from the NASA DC-8, where you can see an intense pollution episode, which is also being contributed to by biomass burning, where there's high relative humidity condition. And so this is a situation where haze is being generated as the particles are swelling, taking up water vapor, and greatly reducing the visibility, which is a big challenge around airports, for example, and other locations where you really want to be able to see clearly. Biomass burning is another example of where water and ambient aerosol interact significantly. This is a satellite image taken off the west coast of the US back in 2009. So this is Southern California here. And you can see a variety of fires with their plumes being advected over the ocean in this traditional easterly flow condition where we tend to have strong heating. Biomass burning is combustion, and therefore it releases a lot of water vapor. The high relative humidity in the biomass burning plumes interacts with the soot and organic containing aerosols, and it changes their size, changes their chemistry, and ongoing gas to particle conversion within the plumes continuously converts gases that are in the plume to aerosol mass. And this is often facilitated by the fact that the particles are growing at the high relative humidity condition and becoming larger droplets, providing more surface area for the conversion of gases to aerosol mass. This particular example is especially important for people that live downwind of sources of burning. I know this is a significant issue in India. This is becoming a bigger and bigger problem in the western US, where we're having intense fire seasons. And these biomass burning plumes, as you can see in this photo, they can merge and they can become their own cloud complexes. So they can generate sufficient relative humidity to actually create their own clouds, which becomes another effect, a so-called indirect effect, where aerosols, the modification of aerosols, or the injection of higher concentration of particles into systems where clouds are going to form could create clouds, for example, that are brighter to the sun. So, for example, they're more reflective, which could produce a climate forcing effect. Finally, I want to show a picture taken out of a climate change report, again from NASA, which shows the advection of a dust plume in the upper right-hand corner here, being advected off the Sahara Desert over the mid-Atlantic, and then it's being captured by LIDAR. That's what these vertical sheets are, as it's advected over a 1-week period all the way over to Mexico, the Gulf of Mexico over here in the lower left. And where you see these D letters, that's actually symbolizing the dust plume. This is also an important process for India, as I believe there's quite a bit of dust that's advected from Africa to India, and it can provide an important input to the ocean as well as to the Indian subcontinent. My point in showing you this photo is that plumes like this, dust is typically considered to be relatively non-hygroscopic, meaning it doesn't really respond to changes in relative humidity. It doesn't change its size. It doesn't really take up a significant amount of water. But in this case, the transport of the dust from the Sahara over here in the top right can happen over such long time periods that there's a significant amount of time for gas to particle conversion, for example, to convert nitric acid or other gaseous species to aerosol nitrate or even sulfate on the mineral. The mineral then becomes much more hygroscopic, meaning it can take up more water and change its size and facilitate further chemistry, or modulate its lifetime in the atmosphere as perhaps its settling velocity increases under high relative humidity conditions, and therefore the dust is lost to, say, the ocean surface, where it can actually serve as a significant source of iron to trigger other processes that go on in the ocean. So aerosol hygroscopicity, or the reaction of particles to changes in relative humidity, is a fundamental property, thermodynamic property of aerosols that really needs to be understood, because it's such a key part of defining particle size as relative humidity changes, and also the chemical processes that can significantly alter aerosol mass. So what is hygroscopicity, and how can we calculate it? So as I've mentioned, hygroscopicity really is the response of aerosol to a changing relative humidity, for example, a changing water vapor environment. Some particles in the atmosphere acquire water vapor at higher relative humidity and grow significantly. For example, sodium chloride or sulfuric acid grow by factors of 3, 4, sometimes even 5 at high relative humidities, above 80%, approaching 95%. There are other types of particles in the ambient, like soot or fresh tar-like substances that come out of some biomass burning sources that hardly grow at all. Perhaps you expose it to 85 or 90% RH, and it only grows by less than 10% in size. So how are we going to understand such a complex system represented, for example, by this size distribution cartoon that I've created? This size distribution represents the complexity of the system that we're trying to understand, trying to predict the hygroscopic growth of. The challenges here are formidable. We have a situation where we have a 4 order of magnitude variation in particle size. We may have up to a 6 or 7 order of magnitude variation in concentration here on the y-axis. And then at any given size, depicted by these different colors, we may have particles with different chemical compositions, where I've created a hypothetical situation where in this nucleation mode down here between 1 and 10 nanometers, we may have a significant sulfuric acid component represented by these red bars. There may be organics coating those sulfuric acid particles represented by these green bars across a much, much broader size range. This is very typically found in internally mixed particles, meaning particles where multiple chemical species are present within an individual particle. We have other types of particles at any given size. We could have carbonaceous particles here represented in purple across a broad spectrum. We may have sulfate particles here in accumulation mode represented by the orange. We have sea salt particles and mineral particles. So nitrate as well. My point in showing you this is that the aerosol that we typically want to sample in the ambient can be quite complex. And the chemical composition at any given size could have 10 to perhaps even 100 major species that could play a role in determining how those particles respond to increasing relative humidity. So how do we determine how these particles are going to respond to elevated RH? So one tool that we use is called Kohler theory. Kohler theory is one technique that can be used to predict how a particle size will change at a given relative humidity. And just to extend, just to extend this concept of what happens when you take, for example, a 100 nanometer particle right here. If you expose 100 nanometer particles that you've been able to reach into the size distribution and just pick out those 100 nanometer particles, what would we typically see if we expose those particles to an elevated humidity? Well, that's what I'm trying to depict down here in the lower part, where here perhaps is just the dry diameter. In the dry diameter state, we still see the same kind of mixing of these 3 major chemical constituents, sulfate, carbonaceous, and organic particles, all more or less of the same size. But then what often happens when we expose these particles to elevated humidity, in one instrument in particular, the humidified tandem differential mobility analyzer, or HTDMA, which is a product that we produce, what we typically see is we see this dry mode all of a sudden splits into 2 different size modes, where we might see a more hygroscopic mode, a mode that maybe grows by 50% or 60% at 85% RH, and a less hygroscopic mode, where here perhaps we have the carbonaceous dominated particles that are simply less hygroscopic. So this type of information is very difficult to discern from bulk methods, because bulk methods don't allow you to simply look at one size particle. They would typically look at this whole mix of particle sizes all at the same time. Whereas with an HTDMA and other approaches, for example, we can look at individual particle sizes and see how relative humidity changes the size, even though the initial size was only one dry size. So Kohler theory, let me explain briefly here, is the fundamental theory that's used to try to calculate how particles are going to respond to elevated humidity. It's typically composed of two terms. There's the S of D is really just RH, and the statement here is that the equilibrium RH for a droplet of dry size D is a balance between two factors. It's a balance between a water activity term, the Raoult term, which is this A sub W term, which is a chemistry-dominated term, and this exponential term with the surface tension in it, which is this term right here, the Kelvin term. So you can see that the Kelvin term goes as the inverse of the dry size. So it's really about the curvature effect of the particle. As the particle gets smaller and smaller below, say, 50 or 40 nanometers, it becomes smaller than the mean free path of the water vapor molecules in the atmosphere. It becomes harder and harder for the water vapor molecules to physically find themselves attached to the surface to initiate the condensation process. And so as the dry sizes become smaller, the curvature becomes larger. This term gets larger and larger, and the equilibrium RH required to actually condense water vapor onto that dry particle gets higher and higher. So that's typically only important for sub 50, 60 nanometer particles. The second term, which is this water activity term down here, is the much more interesting one for atmospheric applications. And it has terms like the molality or the concentration of the droplet, the number of ions that are actually in the solution, the droplet solution being created. And the way to think of this second term is really when a droplet forms around an aerosol, the water-soluble material begins to dissolve inside the water that's condensed onto the particle. Ions are distributed throughout the water solution, and some of them are at the surface of the droplet. The ions are displacing water locations on the surface of the droplet, which means it takes less water vapor to actually maintain the equilibrium condition of the droplet, because the effective surface of water molecules is reduced over that droplet. So the action of chemistry is to actually reduce the relative humidity required in equilibrium over a droplet. Now, let's add water. If we add water to this size distribution, you get the effect shown by this light blue line. The whole size distribution in general shifts to larger sizes, and that shift is different as a function of size, controlled primarily by the size of the dry particle as well as its chemical composition. In this case, if we want to begin to relate theory, Kohler theory, for example, to the measurement of water activity or the wet size, we can simplify the theory that I presented on this previous slide to rewrite it in terms of things that we can actually measure. So remember, here is an equation showing the relative humidity on the left, but I've rewritten it in terms of the dry diameter, D sub D, shown here with the blue circles, and the wet diameter, just D. So we can measure the relative humidity of a sizing measurement. We can measure the dry size that's being selected, for example, with the HTDMA technique, and we can measure the wet droplet size that is also measured, for example, with the HTDMA or another wet measurement technique, to actually obtain all of the parameters on the right side here, except for this one, so-called kappa. Kappa is a parameterization that tries to take into account the effect of chemistry on the equilibrium RH over the measured droplet. Kappa is a function of the chemical composition of the particles that you're sampling. It's not known. But if we obtain enough data of this manner, where we perform sizing studies at various relative humidities, we measure the wet droplet size, and we know the dry size we picked, we can actually derive kappa from a set of equations defined by these measurement results. Let me move now to a broader scope, thinking more around the scientific needs with respect to hygroscopicity. And then I'll return in a bit to concepts like optical closure and aerosol cloud interactions, trying to frame those needs with respect to the overarching questions here. So one of our goals in being able to measure wet aerosol state is to help constrain climate change models by producing data that will help them do a better job of parameterizing this effect. So sustained measurements are required, not just at the ground, but also aloft through vertical profiling, to help produce data sets that are representative of the broad spectrum of aerosol conditions that climate change models need to model. So within what framework can we perform these measurements in ways that climate modelers are going to accept the data? The data have to be of good quality, and they need to represent reality. So one way to perform these types of measurements is to bring together in situ measurements, detailed microphysical, thermodynamic, and other in situ style measurements. Bring those together with bulk measurements like a nephelometer and light absorption measurements, and to see whether or not we can predict the bulk measurements like a light scattering or light absorption coefficient measured by a nephelometer or an absorption photometer, whether we can predict those bulk measurements using measurements like the size distribution and the wet response of the size distribution, how the size changes, some chemistry measurements on the refractive index. So these sorts of closure studies help educate us whether we're really understanding all the components that participate in the radiative transfer that happens by virtue of the aerosol obtaining water. Aerosol cloud closure is another approach that can be taken when you're thinking about understanding wet aerosol forcing. Aerosol cloud closure means performing measurements, for example, of below cloud base aerosol hygroscopicity and cloud condensation nucleus activity. Performing in-cloud measurements, for example, using a UAV platform or an aircraft, or perhaps balloon-borne measurements, where you can actually look at residue particles from the droplets by sampling them carefully to understand which particles participated as nuclei and which particles did not. So being able to model the activation of particles in real clouds is another key component of extending the hygroscopic growth measurements into the supersaturated regime. Longer term types of measurements involve validating satellite retrievals. So satellite data is becoming more and more quantitative, and it's global. Climate change modelers are looking to satellite data for guidance for how to better their models so the models produce realistic results. It's our job as in situ measurement people to validate what the satellite is measuring. And finally, regional ground networks and long-term measurement studies are required for us to truly give climate models a temporal representative data set of aerosol properties. So how can we actually perform radiative closure, and how does hygroscopicity factor into this? So we can use an equation like this one, for example, where on the left side here, you see the extinction coefficient as a function of wavelength of light, for example. The extinction coefficient is just scattering plus absorption. So this can be measured directly with a variety of instruments for a given input aerosol. It could be measured also as a function of relative humidity by those instruments. On the right, we have the in situ measurements that are more detailed. So, for example, we need to measure the size distribution, dN d log d. We need to measure that dry. We need to measure it a variety of RHs representative of the ambient. We need some measurement, or at least good theoretical calculations of the mass extinction efficiency. This is often given by running me theory code, for example, but in order to calculate that, you need to know something about the refractive index, which means you need to know something about the diameter and the chemistry of the particles, which all change as a function of RH. So again, just thinking primarily in the dry state, you need the number size distribution, refractive index, and particle extinction efficiency just to do this type of closure study where we can do the calculation of all these, using all these parameters over a range of diameters on the right side here, and see how well can we actually calculate what was measured by a bulk instrument. Now, if we add water to this whole setup, what happens is we need to recognize that the diameter is a function of relative humidity. So we need to include the effect of water if we're trying to do this closure study under ambient conditions, for example, in a column underneath a satellite pass. We need to do it at the relative humidity representative of the different layers in the column that we perform the measurements. The size distribution, as I showed earlier, also changes with relative humidity. Particles will grow. That shifts the size at which the counts are allocated. The extinction efficiency is also going to be a function of relative humidity because the diameter changes as a function of RH. And the refractive index is also a function of diameter, and the chemistry is also going to be altered by the addition of water to the system. So things get more complicated when you add water to the picture, but that doesn't mean we can't do it. It just means it's a little bit harder. So in this case, we need pretty much the same parameters that we needed for the dry closure calculations, but we need these parameters as a function of relative humidity as well. So how can we measure this? So there are a variety of techniques that can be used to approach a problem or questions around optical closure. One fundamental measurement is to be able to measure the size distribution, for example, using a mobility-based method, using, say, a differential mobility analyzer, and optical particle counters together to measure a broad spectrum of size, doing that at controlled relative humidity conditions. You also want to do dry measurements or cycle the same set of instruments between dry and wet conditions to understand the role of water in changing the size distribution from its base dry state. To put the first two measurements in context, and because the mixing state of particles is so complicated, HTDMA size-dependent water uptake is often also necessary. And the reason for this is that as particles are transported through the atmosphere, they're often chemically altered. They're oxidized. The atmosphere is essentially an oxidation reactor. And as the chemical composition is altered, as new material is added to those particles, typically their hygroscopic growth changes. Sometimes they're rendered more hygroscopic, sometimes they're rendered less hygroscopic. It all depends on the chemistry that's happening during the transport of the particles. In order to understand whether or not particles of a given size are all responding to the same as a function of RH, meaning they're internally mixed, that means particles, individual particles at that size all have the same mix of chemical species in them. Under those conditions, you'd expect all those particles to respond the same when they're exposed to relative humidity. But in most situations, what we find in the ambient is that the particles of a given size exist in multiple chemical mixing states. And there are some particles, for example, that just contain sulfate, organics, and nitrate. And then there's another subset of particles within that size range that contain soot and organics, and perhaps a very small amount of water-soluble material. Those two populations are externally mixed. And those two populations, when you expose them to relative humidity, are going to respond differently to RH. The more hygroscopic particles might grow by a factor of 1.5, and the less hygroscopic particles might only grow by a factor of 1.1 or 1.05. And it's the HTDMA that will reveal that for you. The bulk measurements or the polydispersed size distribution measurements can't tell you anything about that. There are other tricks that we can play to get at the refractive index of the particles, which is another parameter that we really do not have a direct measurement for. You can run an optical particle counter, wet and dry, behind a mobility spectrometer, where you select out a single size and deliver it to the OPC, and you between those two, you know two different sizes, and you can actually derive an effective refractive index for your particles at your sampling site. Size-dependent chemistry is another important input to these types of calculations, these types of measurements. On the bulk measurement side, we often see people running wet nephelometers or wet-dry nephelometers, size-dependent absorption to get at the extinction coefficient. And again, we can't just do this on the ground. We need better tools to actually do measurements aloft. Vertical profiling is going to be key in future climate change model validations, and we think UAVs are a wonderful platform for that. We've been developing a humidified mini scanning DMA system, as well as a humidified mini OPC that can be operated from relatively small UAVs that we think could contribute significantly to understanding how water alters particle properties up in the atmosphere. So these measurements are needed not just at the ground, but also aloft, continuously, and I would argue focused within satellite columns, and I'll get to that in just a moment. Now let's move to a second area that hygroscopicity impacts significantly, aerosol cloud closure, or the indirect effect, so to speak. How can we calculate it? Again, we're going to use Kohler theory, and the simplified form of it is shown here, again, just as I showed earlier. In this case, what we want to do is we want to take results, for example, of relative humidity on the x-axis here and drop diameter on the y-axis, where you typically see this increase in droplet diameter with increasing RH. And we want to extend those measurements beyond the subsaturated range that you typically see in measurements like the HTDMA. We want to extend those measurements to above 100%. The Kohler theory is perfectly valid. In fact, it's more valid up in these higher RH ranges, which are representative of the supersaturations above 100% that you might find in clouds. And so what we would typically do is we would measure the relative humidity, S of D, and the droplet size, D, for a given dry size. This is what's done in the HTDMA. So, for example, that would be one of these points on this curve. We have a fixed RH, we measure the droplet size, and we've already fixed the dry size in the measurement. Once we have a set of points to define this curve, we can actually fit the Kohler theory curve to these points. That's what's shown as these dark lines here. And once we fit this, we determine the best fit kappa value that explains these growth data. And once we've derived kappa, in theory, we have all the data we need to calculate this entire curve, even up into the supersaturated range. So we can derive the CCN spectrum from the measured size distribution, and we can derive the cloud drop distribution using models. So this can be compared with results from the CCN, for example. The bonus in doing this work is you can also use these same data to do wet and dry optical closure, as I've discussed in the previous slides. So how can we measure this? Thinking about aerosol clouds, how can we measure this? A lot of the measurements are the same as before. You need both dry and wet mobility and OPC number size distributions, the humidified TDMA, the CCN instrument to understand the kind of in situ droplet activation characteristics. These measurements can also be done now from UAVs. But here we have a new tool, the so-called CVI inlet, or counterflow virtual impactor inlet, to actually measure cloud droplets in real clouds and evaporate all the water, leaving just the residue particles to be able to discriminate the particles that form droplets from those that did not. We have a ground version of this that we've developed, and we're working on a unit that could be deployed on UAVs. And this is where light, small, and cost-effective devices for UAVs comes into play. These studies need to be able to make, we need to be able to make these studies in real clouds. Research aircraft can do this. They're extremely powerful platforms, but they can cost upwards of $5,000 or $6,000 an hour to operate, which means you can only deploy them for multiple weeks at a time before most budgets are exhausted. UAVs, on the other hand, can be operated down in the several $100s per hour range. You can typically operate more of them. They're a less expensive platform. Overall, the logistics is much easier operating the UAV compared to, say, a King Air or a larger research aircraft. So our whole goal here is to bring the in situ measurements and cloud sensing measurements together to be able to close them, to calculate the cloud properties from the measured in situ properties. And again, we want to be able to connect measurements at the ground to what was observed above in the cloud. And we need to be able to connect those two. So we need measurements between the cloud and the ground in order to really understand exactly what's going on. And again, I would argue, focus these measurements within satellite columns during satellite overpasses so that the data can also be used to help constrain satellite retrievals and validate them. There are other applications for these types of measurements, looking at changes in precipitation patterns with time, or looking at the physics of precipitation. Obviously, air quality, visibility is another application for these types of measurements. So the challenge here is we have a lot of complicated simultaneous measurements to perform. And just because it's hard doesn't mean we shouldn't do it, but because it's hard means we need to be smart in how we do it. And that's actually where we as a small company work quite closely with all of our customers, helping them design inlets, helping them design humidification setups, automated switching valves so you can use the same equipment for your dry and wet measurements. But there is a lot of care that needs to be taken to exactly how you sample the particles so that you know your sample is representative of what's going on out in the ambient. So I've mentioned this whole business of trying to do these measurements coincident with satellite overpasses. And this so-called A-train, championed by Ralph Kahn and others at NASA, is a great example of a set of satellites that all move over the Earth in essentially a train of satellites, over an 8-minute period. In this case, the times that are represented here, they pass over the equator at roughly 1:30 p.m. local time. But if we could design experiments, for example, in India, coincident with the overpasses of these satellites, so that all of the data that were acquired, we knew that there would be archive data of all these satellites to allow us to bring together the satellite data and the in situ data, the detailed data from, for example, networks of ground stations or with simultaneous UAV vertical profiles. This would be an extremely exciting scientific endeavor. So this is what that might look like. For those of you that saw my talk at the International Aerosol Conference, or the Indian Aerosol Conference in 2016, you might remember this figure. This is a concept that I think could be quite powerful. It actually builds on the ACE series of experiments that were funded by the National Science Foundation and many other agencies back in the 1990s and the early 2000s. The concept here is to design a set of sampling sites, here depicted by a red supersite surrounded by smaller green network sites, right along the track of the satellite. So here's the satellite moving over these sequence of different networks, doing ground-based measurements. And at each one of these super sites, if one or more UAVs outfitted with the appropriate equipment could be continuously vertically profiling, as depicted here by these red arrows, as the satellite is passing over, then we've begun to build the data set required to really look at the parameters that are being derived from the satellites and compare them to what's being measured in the vertical profile, as well as at the ground. So these are important types of measurements to make in a coincident fashion, because together these measurements all support each other. For example, the UAV vertical profiling not only helps in deriving parameters that can be compared to what the satellite believes is going on in the vertical column, but it also puts the ground network results in context. It allows the extension of the ground-based sampling results into the vertical, which can be very important even for local or regional scale questions around visibility reduction, around changes in precipitation patterns, and those sorts of questions. So, just to conclude, some future directions that I would like to throw out for your consideration. What are some key needs coming up in the near term? We need to design our measurements so that we quantitatively connect aerosol to cloud properties. We need to develop clear questions that can be answered by our measurements, not questions that are beyond the capabilities of our measurements. We need to design our measurements so that we can answer the important questions that we have around aerosol cloud interactions. And new tools are coming online. Excuse me. We're helping to develop some of them to allow these kinds of connections to happen more quantitatively. It's only when we have that level of data that we're going to be able to design the future instruments that are needed to answer the questions we still can't answer. We need to make a commitment to long-term measurements. I realize that this is a significant investment, but long-term measurements are going to be key to really putting the data sets that are used to constrain climate change in context. Climate change models can't use 2-week data sets to validate a 400 by 400 kilometer grid box result. They need climatologically relevant data sets. We need to do a better job constraining remote sensing retrievals. And the reason I'm fixated on satellites is that more and more climate modelers are turning to satellites as ground truth measurements to help validate their models. And satellite data is improving, by all means. But we still need to validate what the satellites are telling us. And that's where we, as in situ measurement researchers, it's our responsibility to step up and provide that validation. The development of portable, more cost-effective instruments, I believe, is going to play a key role in facilitating these above points. Collaborating across disciplines and countries is going to be critical. These problems that we're starting to face, these questions that we're starting to try to answer, are multidisciplinary, and they change with region. And there's some conditions, for example, the monsoon in India is a complete unique climatological condition that absolutely has to be properly simulated in climate models. But it really happens in India, and it happens because of the specifics of India. And so partnering together with people across boundaries is going to be critical to bringing in the expertise required to help, not just in India, but in the Arctic, in the Antarctic, and other places in the globe. And finally, just a reminder, I know all of you know this, but climate change is coming. I think there's finally becoming a much broader awareness, and it's up to us as part of the solution to deploy these instruments to help create better climate models. And I know that 20 years from now, I want to be able to say, I contributed to this. I know all of you do too. And making tomorrow a better world is important for all of us. Thank you very much for your attention.
Thank you, Fred, for this wonderful presentation. So now we will have a question and answer session. So got few questions from attendees. First question is from Mercy. So she is from IITM Pune. They are having both HTDMA and CCN counter at their observatory. So she's telling that many times it is seen that the kappa values derived from HTDMA and CCN are not matching. So can you give a suggestion to them? What is the possible reason for this?
Yes. So let me make sure I understood your question, because the audio is breaking up a little bit. The question is, this kappa parameter that I described early on in the presentation, if you derive it from HTDMA results, and then you try to compare it to values that are derived from CCN results, they don't match. Is that the question? Sachin? Sachin, can you hear me? I seem to have lost my audio. So I'm not sure if people can hear me anymore. Maybe I'll proceed assuming that people can hear me.
Yes, yes, we can hear you.
Okay, sorry, I didn't hear anything, so I thought I was disconnected. So the reason the kappa values don't match always is that the droplets that are formed inside the HTDMA have a much higher concentration in them, typically, of this chemical species than in the CCN. The CCN is operating at humidities above 100%. The droplets are significantly larger, typically. And the kappa parameter is a quite deep simplification of the chemical composition effect in the Kohler theory. So there are a lot of parameters that are kind of buried into this single kappa value. So for example, if you have a droplet that has formed around a particle, the water-soluble ions have dissolved into the solution, and the ions are interacting with each other because they're oppositely charged or they're similarly charged, and they're going to the surface of the droplet, and that affects the interaction of the RH with the droplet, as I explained earlier. So the solutions are somewhat more concentrated, and the assumption that you can model the kappa from in the supersaturated state using subsaturated data can be problematic depending on the chemical composition of the particles that you're sampling. So in that case, there are extensions to the simplified kappa theory that could be attempted to try to better model the true kappa under the subsaturated conditions to match what's happening in the CCN device, where the droplets are much bigger. So the solution is much more dilute. The ions are so far apart, the ion-ion interactions are not nearly as important. So essentially it's a kind of a disconnect between the assumptions that are made in kappa theory, where the simplified theory, in my opinion, it has some issues with the subsaturated HTDMA growth. So that's where being able to do HTDMA measurements at the higher humidities is important, and that's where you only want to use the higher RH range of the HTDMA to derive the kappa values to at least get closer to that dilute droplet state.
Yeah, thank you. The next question is how the surrounding temperature plays a role in activation of an aerosol into a droplet. So what is the role of external temperature in the activation?
Right. So that's an interesting, excuse me. That's an interesting question. So if you recall the equations I put up for the Kohler theory, temperature is explicitly in the Kelvin term, the curvature term. Temperature also indirectly affects, often in the ambient, the relative humidity, because as most of you know, at nighttime, as the temperature typically drops, the relative humidity is going up. That can drive more water onto the particles. So it's that temperature oscillation, that diurnal oscillation that at least we see here in the mid latitudes. Now, closer to the equator, it's much, that oscillation is much smaller, but it still drives variations in relative humidity in the ambient that swell the particles, and then when the sun comes out and things warm up, the relative humidity drops, and you tend to see the droplets shrink with time. Temperature also has other effects that I think are more second order, that might have to do with surface tension or other kind of chemical processes, chemical reactions within the droplets could be strongly temperature dependent. So temperature is important. It's often kind of taken for granted that you just know it, but the condensation and evaporation process at the droplet surface itself can modify the temperature field around droplets. So there it gets a bit more tricky, understanding, what's the right temperature actually to be considering.
Thank you. The next question is, if we know aerosol, the properties of aerosol, how it is behaving in the subsaturation, then can we predict how it can be behaves in supersaturation conditions?
Yes, you can. So that was what I was trying to describe in the slide where I had all the red arrows with the different steps, where from HTDMA results for for aerosols with a relatively understood chemical composition, you can actually derive this kappa parameter either using a simplified kappa theory or in some of my previous work many years ago, I actually used a two-parameter model to derive the unknown chemical composition dependent parameters that affected the hygroscopic row. Excuse me. So once you've derived these chemical composition dependent unknown parameters, because remember, when you take your measurement out to your sampling site, you don't necessarily know the properties of the particles that are coming in. And so you can use a CCN device to measure the droplet number at a given supersaturation for the particles that you're bringing in. So for that supersaturation, it'll tell you, oh, this is how many droplets formed. And then if you have an independent number for the total aerosol, you can ratio those two to get a fraction, an activated fraction. But if you want to really be able to predict the cloud nucleating activity potential of a size distribution of aerosol, by picking out different sizes of particles across the size spectrum representative of the different modes in the size distribution, and exposing those particles to a sequence of higher and higher relative humidity, as close to 100% as you can derive data that you can fit to obtain these chemical composition dependent parameters. Because you don't know the chemistry of these particles unless you have some single particle mass spec or some other kind of mass spec based instrument. And even if you do have those chemistry measurements, you often don't have them in as detailed a fashion to give you the mixing state and to tell you how one mixing state and another, how they responded to relative humidity. So, it's complex. But you can, by fitting to the Kohler model to, for example, HTDMA measurements, you can extend the results to supersaturated conditions to begin to understand how those particles would behave in a supersaturated environment. With the caveats, for example, Mercy mentioned that there are some inconsistencies with the simplified kappa model, where the kappa derived in the way I just described from an HTDMA data doesn't necessarily agree with the kappa derived from measurements at different supersaturations with the CCN spectrometer. So those are things that really should be studied in more detail.
Thank you. The next question is from Suresh Kumar Reddy. So he is asking that what is the maximum relative humidity that we can use in HTDMA, and how the uncertainty vary at higher relative humidities?
Mm-hmm. So the answer to that question has something to do with the environment within which the HTDMA is operated. So when we operate the HTDMA in our laboratory at the factory, we're able to maintain 93% RH as the maximum value under carefully temperature-controlled conditions. So when you operate an instrument at high relative humidity, the practical issue is the temperature variation, usually. What it means is that if the temperature drops more than, say, a degree in 1 hour, the instrument is made of a lot of metal. It has difficulty staying or matching that change in temperature with time. And so the variation in temperature eventually can cause localized cooling within the instrument that can cause the 93% RH to jump up to 97% in an uncontrollable way, which is not what you want. If you get too close to 100% RH, you can induce condensation within the instrument, and liquid water inside of instruments is generally not what you want to have. It's going to create issues. You certainly can't control relative humidity accurately if you have liquid water at various locations within your sample line. So 93% is the maximum value that we've determined from our studies that we can operate when we have a well temperature controlled environment. In some cases, at field sites, that can be a challenge. And in some cases, 90% is really about as high as capable in a reliable way. The limitations there are, not just with temperature, but also just in generating fully saturated air at the flow rates that are required within the HTDMA. But even at 93%, our own findings have been is we can maintain the plus or minus 1, maybe a little bit over 1% RH with time.
Yeah, thank you. Fred, one last question we will take. It is again from Mercy. That if we have a HTDMA and we want to do various experiment, then what factors to be considered before selecting the dry sizes, that is the sizes from the first DMA, and the RH values when we are using the HTDMA?
Mm-hmm. So the answer to that question has to do with a couple of different things, two main things. The first is, what's the question that you're trying to answer? So if you're trying to answer questions around light scattering or light extinction, or you're trying to answer questions that maybe have to do more with accumulation mode or coarse mode particles, then you would select particles with the HTDMA that are probably larger than 100 nanometers. With the HTDMA, you can actually select up to 2 micron particles. So that's a unique feature of our system because of the design of the DMA. You can't select 2 micron dry particles, but you could select 1 micron dry particles. You could even select 1.5 micron dry particles if you were studying things like dust intrusions, dust transport into the Indian subcontinent, and you wanted to examine, how hygroscopic are these particles. You could scan up to 2 microns and at least capture any kind of hygroscopic growth between 1.5 and 2. So your question should really drive the sizes that you want to select. So as another example, let's say you're really interested in particles that were just formed, so very small particles. You may select 10 nanometer particles. That's about as small as we really can realistically go with the HTDMA. So, you might set the dry size to 10, 14, 18, 22 to really study the Aitken mode well. And then you set the downstream scanning size distribution. You might scan from 8 to 50 nanometers for all those different sizes, so that the size distributions are more or less over the equivalent scanning range. And then you'll pick the relative humidities that, again, are driven by your question. So if you're trying to ask, how do these particles respond in the ambient, and you know that your ambient relative humidity varies from, say, 60 to 90+%, well, then you would design a series of studies where you'd say, okay, I'm going to do a dry study, so dry to dry. That's nice to do because you test that both sizers are sizing properly. And then you may jump to 60%, you may do 60, 70, 80, 90, and then go back to dry. The way the instrument works, it automatically will cycle through all these different experiment configurations that you design. So the second part of the answer to your question has to do with, what does your size distribution look like? So if you're looking at your ambient size distributions and you can see that you almost never have any particles smaller than 20 nanometers, then the design of the study I just gave you would not make sense. You wouldn't measure 10 nanometer particles because they're simply not really there. They're not relevant to your particular sampling site. So learn about by by fitting modes. For example, fit log normal modes to your climatological data, your long-term size distribution data, and look at seasonal trends. Within seasons, look at diurnal trends. Get a sense of what are the dominant modes in either number, area, or volume, and then choose the sizes that define those mode peaks. That would be another approach. And so you might choose not the number modes, but perhaps area is more important for your particular question. Again, it all has to come back to the science you want to do. So always start with the science question first. And then say, you know, if you're interested in gas to particle conversion, then surface area of the particles may be the most critical parameter. So then you may want to pick your surface area modes as the sizes that you pick for the HTDMA, because you want to understand how do those modes respond to water. So you may not want to really focus on the sub 150 nanometer particles if they're not contributing significantly to the surface area. So these are the sorts of things that we are very happy to work with our customers on over the lifetime of our products, designing experiments, understanding the context of the sampling site, and extending the measurement capabilities to help answer new questions. Those are the sorts of things that we really enjoy doing as a company. And just myself personally, it helps me do a little bit of science. And so, you know, please, if some of my answers didn't quite make sense, be sure to get back in touch so I can try and clarify, and we can move forward from there.
Thank you, Fred. We have a lot of questions, but we are already exceeding our time limit. So probably we will send the answer of these questions on the registered email IDs. So let me repeat for all the audience that we will send our presentation as well as the recorded version of this webinar to you on your registered email ID. So thank you again for joining us. Thank you, Fred, for this wonderful presentation.
Thank you for having me.